Howdy. Welcome to the Texas A&M Virtual Engineering Showcase. My name is Jesse Rosa Brodnitz.
And my name is Shanley Mullen. And
we are the proud creators of VALE. Have you ever arrived at a place only to not know where a room is? Or maybe you don't like going through the trouble of asking someone for directions when you're running late to a meeting. What about when building maps are not the most clear and you're in a hurry?
Every day, there are people struggling to get around large, complex buildings, such as hospitals, schools, retirement homes, or even large companies like Pixar. These places usually have to provide a map for its guests, and sometimes even for employees. Although, as many of us know, these maps can often be cumbersome and confusing, making navigation a chore. That's where VALE comes in. VALE will act as a mediator between the user and the building to guide them around without the need for complex maps or systems. All someone will need to do is type a location in and VALE can take them there. VALE is an autonomous robot that can lead you to your destination. VALE is a great listener and good with questions. Using advanced techniques and calibrations, VALE will simply ask you where you want to go and listen for your answer.
Using the TIMS 781 LiDAR produced by SICK, the BeagleBone Blue computer, and a robot base produced by the Texas A&M MXCT department, VALE takes your input and leads you to where you want to go on a single floor of the building.
VALE is designed with the disability and elderly communities in mind, first and foremost. These communities represent 28% of all Americans. Many members of these communities are reliant upon those around them. VALE exists to change that by offering independence back to those communities.
Operation is broken up into two phases. Phase 1. VALE works by creating a 2D map of the building using the LiDAR and odometry. The robot takes a scan with 27 data points and reorients the zero position to be pointed straight ahead. At this point, the data is split into a 2-column array containing the distance and the angle. Any data with a distance that is less than the width of the robot is filtered out. Next, the entire array is passed through a function that relocalizes the data with the robot's y-axis, based on whether or not the reading is positive or negative. All the data is then converted into global coordinates from where the robot is currently situated. From here, the odometry data is taken to calculations of the wheel rotations. The odometry program returns an array containing the global x position and global y position, and the orientation of the robot calculated through odometry, along with a corrected compass reading. As the robot moves, additional scans are taken, and the position of the robot is updated with the odometry. This in turn causes all the future data points to register with the robot's new position. The odometry program pulls data straight from the encoders in order to calculate the current position and orientation of the robot. This is achieved by first taking two encoder readings separated by a small time step. The difference between these encoder readings is taken and the amount of rotation on each wheel is calculated. The updates in the wheel position are then averaged to give the distance the center of the robot has traveled and the change in angle of the center. The robot's x and y locations are then calculated based on the old position of the robot, the change of the distance traveled of the center, and the change in angle. This is then formatted and output as an array with the angle of the robot and a magnometer reading. Magnometer is used to give the initial reading for which direction the robot is facing, and is then used to correct large deviances through an accumulated error in the angle. This is done by taking an initial scan of the floor in its entirety and converting those points to Cartesian relative to the robot. The local Cartesian points are then converted into a set of global coordinates for the environment. From here, the robot tracks the number of rotations on each wheel to determine the distance traveled and utilizes this to update the robot position for future scans. When an entire room is mapped out, the map is stored and the room points extracted as possible destinations. Phase 2. The next phase is the implementation. It also excels at obstacle avoidance. Using the LiDAR, a scan is taken and the LiDAR and angle are recorded in an array. How close the obstacle is determines the severity of the reaction. The angle is used to determine if the object is to the left or right of the robot. A level-based system is put in place for this. The levels are the following ranges: beyond 2 meters, between 1 meters and 2 meters, between 1 meter and 0.5 meters, and less than 0.5 meters. The robot will undergo no action if the 2 meter range is exceeded. If the obstacle is between the 2 meter and 1 meter range, the robot will commence a gradual curve. If the object is between 1 meter and half a meter, a medium turn will be conducted. If it is less than 0.5 meters, block motion will be conducted. Implementation starts with the user asking VALE to be taken somewhere. VALE, would you please take me to the bathroom?
VALE responds, "The bathroom is right this way. Please follow me."
From here, VALE will travel to the destination. Using advanced obstacle avoidance features, VALE can safely navigate a building and respond to changes in the environment, such as another person or object being placed in the way.
And remember, VALE is your friendly guide robot, so whenever you are lost, VALE will be there for you. Thank you.